Hello, and welcome to today's WJE webinar, Investigating Concrete Failures, Typical Deterioration, or Unique Conditions. My name is Liz Pimper, and I will be your moderator. During the next hour, materials engineer Todd Nelson and structural engineer Josh White will focus on two distinctive projects involving cracks and spalls that resulted from uncommon structural and materials failures. The presenters will discuss the process of conducting a structural and materials investigation and how, in these projects, the investigative process helped identify unique conditions that led to the failure. This presentation is copyrighted by Wisjani Elster Associates. And now I will turn it over to Josh to get us started. Josh?
Thanks, Liz. We're very happy to be here and glad you could all join us today. So we're going to jump right into it. Todd, my colleague, and I will be presenting on two unique concrete failures that we've investigated, and we'll be discussing how our investigation was prompted by owners who were observing and responding to signs of deterioration. So at the time, the owners were perhaps unaware that the conditions that they observed were actually quite unique. But as an owner, a property manager, or those involved in helping address concrete failures, how do you know if what you are seeing is the result of typical deterioration or unique conditions? We hope that this webinar helps to answer some of those questions. Accordingly, these are the learning objectives. And Todd and I will start today by discussing the question, what is a failure? Then we'll review typical concrete deterioration mechanisms and what might be considered unique conditions. Todd's going to summarize the components of an investigative process, and then we're both going to present two case studies of unique conditions where the owner's responsiveness to finding these conditions helped to address the failure. So a question you may be asking yourself is, how do I know if that thing that I see in my building is a failure? Before we go further, we'd like to just discuss what constitutes a failure. What do we mean by a failure? And it's worth discussing this for a moment, since failure seems like a simple word and perhaps a simple meaning. It's very telling that if I go right now to Merriam-Webster online, we have about 10 entries for this word that covers related meanings and their derivatives. But if I were to ask you, the audience, what constitutes a failure, I might hear you say some of these things. Loss of integrity, excessive deformation, stressing a material in its structure to its strength limit, encountering the big one, perhaps only in California, immediate or progressive collapse. And here is a longer definition, a structural system that exceeds a threshold probability of undesirable events. Loss of life or property. The inability of a structural system to withstand intended loads. Falling short. This is one of the 10 Merriam-Webster definitions. And when you got an invitation to discuss failures with us today, no doubt some notable failures in our country popped into your mind, like some of these that you might recognize. But what about this image? And if you can't tell, you can see a crack running left to right about the middle of the screen. You might ask yourself, is that a failure? Concrete materially has failed in tension, and depending on the design, it may or may not be an expected behavior of the concrete. An owner, however, that is not expecting this crack may have the opinion that this is a failure, and so there may be some varying opinions. What about this one? Is this a failure? This might be more convincing because whether you're an engineer or an owner, that large spider crack is not ideal or expected. Looks like we had a little bit of an impact event. But what about this column capital? I don't think there's anyone on this call who would dispute that this is a failure. But even so, the structure is still standing, and even though it is a prominent concrete failure, it's not necessarily a failure of the global system. So you're likely asking yourself, how do I know that that crack in my slab or that spall in my garage is or is not a failure? As you can hopefully see by now, there are many ways to view and interpret a failure, and some considerations include determining if it is purely cosmetic, which may be a form of failure in that it's unmet expectations, or that there are underlying problems and that simple crack or spall you see is just an indication of what's going on behind the scenes. Perhaps in the worst case, depending on how severe the conditions are and where the deterioration is located, you may be concerned about a potential for the collapse of a structural element. In order to provide these answers, we use an investigative process. Todd and I will present two case studies that begin with obvious and not so obvious indications of failures. These case studies will demonstrate that the process is key in understanding and interpreting what we're seeing in the field. In the words of Professor Hardy Cross, paraphrased, strength is essential but otherwise unimportant, meaning that strength is just one of many considerations that structures must consider in design, as well as construction practices, architectural constraints, and the owner's needs. What constitutes a structural failure then is also more than just what simply meets design intent. So let's move on to discuss some common damage and degradation mechanisms. This is a brief list, but it encompasses a lot of the mechanisms you might see in concrete structures. We'll go over a few of these in the next few slides, but the main point here is that failure can be a relative term. It certainly can be catastrophic, but it can also be surface blemishes like on an architectural panel, and it depends on one's definition perspective, and these can both be strength and serviceability related. Another thing to note is that when we have a failure, it is often more than just one contributing factor. So volume change, for example, is one mechanism which can be caused by several factors, and this can result in cracking, unwanted cracking. Chemical attack, which can be caused by various exposure conditions, can result in disintegration of concrete and eventual loss of concrete reinforcing cover. Cement aggregate reactions they're reactions that occur within the concrete constituents, and this can result in paste expansion, pattern cracking, and reduction of the size of a concrete member, and that can directly impact its ability to withstand loads. So last I'm going to talk about corrosion-induced deterioration, which is when specifically we have chlorides and carbonation that work through the concrete and they eventually reach the steel and it causes corrosion. This corrosion can then result in cracks, delaminations, and eventually rebar section loss. So you've got this crack in your structure, and say it's the one we've seen before here, and how do you know which of these mechanisms may be at play? Is it expected behavior and not a real failure? What caused it? Can I leave it alone with no consequence? Should I repair it? How do I repair it so it doesn't come back? I'm going to turn it over to Todd now, and Todd's going to discuss the next steps we take in determining those answers. We're going to call it the investigative process.
Thanks, Josh. I'm going to go through the investigative process that we use to assess these deterioration mechanisms and ultimately assess the significance. And these steps can be applied no matter what the deterioration is, whether it's a crack, whether it's a spall, whether it's a delamination. And the typical first step is initial site visit, where we try to get the lay of the land and get a basic understanding of the problem at hand. Then we typically dive into a document review, which may include review of the specifications, review of the drawings. You know, those drawings that are tucked in the basement in the back corner, those are valuable to us, right? And we may also interview maintenance staff, review reports that have been previously done on the structure. All of that information is reviewed with the idea that we're trying to know as much as we can about the structure prior to a site investigation. So that would lead into a general site investigation where we document the existing conditions. We understand if there's any patterns to the deterioration. We try to understand the exposure conditions, and we take visual observations and document those observations. And that would, and the ultimate goal there is to ask the structure, understand what the structure is telling us so that we can better understand the cause and the significance of any deterioration. From there, we may go into a more detailed site investigation which may include non-destructive testing, material samples. We may collect samples of the concrete to analyze further in the laboratory. We also may make exploratory openings to understand more about the structure. And as part of that, the samples we do collect, we may do some physical testing or chemical testing back in the laboratory to better understand the condition of the structure. And the purpose here is to collect more detailed information for analysis and laboratory testing. Then we take all that information together from the field and from the laboratory testing. We analyze it and reduce the data. We may do some additional analysis at that point, whether that be structural analysis or something else. And in the end, with the end goal, we're trying to help the owner develop repair options or remedial actions for the structure. And that's the investigative process from a very high level. And I'm going to lead that into a project example where we employed the investigative process to uncover a very unique but very interesting problem with cracking of double T beams. And as a little bit of background, the cracking had occurred in double T beams on the roof of a gymnasium. And before we dive into the details of the case study, I'm going to introduce some terminology that I'll use throughout this case study that may help the audience understand what a double T is. So the first part of the double T is the stem, and that's essentially the vertical element of the double T. And the next element is the flange, which is a horizontal element. And the final one is what we call the fillet, which is basically the transition between the flange and the stem. And I'll be using these terms as I discuss this case study. So we got these pictures from the client, and we obviously took a look at the pictures and we saw these cracks. So we're looking up at the ceiling in these photographs with the idea that we have some cracks at the fillet shown on the left photograph. And then on the right photograph, we've got some cracks at the fillet and on the face of the stem of the double T. We got a couple more photographs here, again, showing cracks along the fillet. Based on these photographs, we would guess that these cracks are fairly large. We don't have a scale, but we have an indication that we have some pretty wide cracks along the fillet. And we got a little bit of background information about this project. 11 precast double Ts were fabricated for this project in 2018 and then installed in 2019. As I stated, it supports the gymnasium roof for a middle school. It was also designed as a storm shelter, which is a very important item to understand when we assess this structure. It was designed for ICC 500 storm shelter load, so it was used as the middle school for a tornado shelter. They first noticed this cracking in 2022, so about 3 to 4 years after the double Ts were fabricated. And they were installing some sound matting when they noticed these cracks. They put a no occupancy in place once they saw these cracks, so the kids could not use the gymnasium at all. We were contacted shortly thereafter to help them assess this cracking, employ our investigative process to help understand why they are getting these cracks. So circling back to our investigative process, we employed all of these on this project throughout the duration of our investigation. We started with some laboratory studies, though, and we started with petrography very specifically because our client had already extracted some cores from the cracks at the fillet locations. So they extracted 4 cores and sent them to us to take a look at, and we received those cores and we examined them petrographically. And those who don't know what petrographic analysis is, it's it's a series of observations that our geologists make on cut cross sections of the cores to understand what the concrete is made of, what's in it, and if there's any potential distress mechanisms within the concrete. And the photographs on the bottom show these four cores with the idea that the exterior face of the double T is on the left and the interior of the double T is on the right. And a couple observations can be made on these cores. We see the cracks are wider at the surface and they tend to get narrower with depth, and they're not full thickness as well. So we took a look at those cores petrographically, and what did we find? We found something very interesting, very unusual, but we found microcracking in the cement paste that is characteristic of delayed ettringite formation, also known as DEF. The photograph on the left, which is a cross-section of the concrete that's been magnified to 30 times, you can see these white cracks that meander throughout the paste of the concrete. The white is actually the presence of the delayed ettringite in the cracks themselves. In the photograph on the right, which is magnified, we're zoomed way in, we're magnified at 450x, we can see that these cracks are filled with ettringite, crystals of ettringite that fill a crack. These are classical signs of DEF, and quite interesting and quite unusual for a structure of this type. So what does that mean? So DEF is an expansive reaction within the paste that results in loss in strength and stiffness and eventually leads to cracking. Now, in order for this to occur, we need three things. We have three requirements for it to occur. One being chemistry of the cement or the cementitious materials. We have to have the right chemistry in order for this reaction to occur. In addition, temperature. So we need early age temperatures that are high enough to have this reaction occur. And in the industry, we have some general conservative guidelines that would suggest that early age temperatures have to be less than 160 Fahrenheit. And when I mean early age, I mean within the first 24 hours. We also need sufficient moisture. So the relative humidity within the concrete needs to be high enough, and that's generally understood to be greater than 92%. So we need those three things to occur in order for DEF to happen. So what does this mean for the owner? For obvious reasons, the structural capacity, the current structural capacity is a concern, right? In addition, because this reaction can continue to occur, what does this mean for future cracking and future structural capacity of the double T's? So, circling back a little bit to our investigative process, we did do document review. In this particular case, we took a look at the mix design, and we had reviewed the mix design that was used to fabricate all of the double T's, and that included 900 pounds of type 3 cement. Why is that significant? It's significant for a couple reasons. One is there's 900 pounds is a lot of cement in a mix design. In addition, the type 3 cement is a very fine cement, meaning with the idea both of those would generate a lot of heat during the early ages of the concrete. In addition, we found that the chemistry of the cement was the right chemistry for DEF to occur, which we subsequently verified in the laboratory. We also found that no supplementary cementitious materials were used, SEMs. And this is important because we can include SEMs that will actually help mitigate DEF. We also found that the coarse aggregate was lightweight. And we'll circle back to that a little bit later, why that is important. And we found the design strength of 6,000 PSI. So useful information from the document review. We also, took a look at the drawings, right? And we found that these double T's have 15 pre-stressed tendons in the stem. And the double T's were all cast in the summer of 2018 in a climate that was quite warm. We also learned that the double T's were not externally heated, meaning no external heat like steam was applied during the curing process. We often see issues related to DEF in precast elements when external heat is, like steam, is applied to the product. They did not do that in this particular case. We also learned that paint was applied to double T's once they were installed. And we'll circle back to why that's important later. And based on the maintenance records from the maintenance staff, the relative humidity in that gym was maintained at about 40%. So you may be thinking, well, we need 92% RH for DEF to occur, but a gym's at 40% RH. Why do we have DEF? We'll get back to that a little later. So we proceeded to do a site investigation as part of our process, which include mapping of the cracks, extraction of additional cores for physical testing and additional petrography. We also did some non-destructive testing, ground penetrating radar, internal relative humidity testing, and ultrasonic pulse velocity testing. So the crack mapping that we did, and we mapped all of the cracks on every single double T. We found that 9 of the 11 double T's had cracking, meaning they had cracking at the fillets or potentially on the face of the stem. So there's 2 of them that do not have cracking. And the crack width varied from 15 to 125 mils. So 125 mils is a pretty wide crack. That's about 1/8 of an inch. So our suspicions were verified that some of these cracks are very wide. So as part of the site investigation, we did do GPR, ground penetrating radar. For one reason, we wanted to verify the location of the steel versus the design. We wanted to make sure it was constructed consistent with the design. We also wanted to locate the reinforcing steel to avoid it during our core extraction. And we also did internal relative humidity. Again, we wanted to know what the internal relative humidity of the concrete was to see if it was consistent with the formation of DEF. So we installed 3 internal relative humidity reports on internal relative humidity probes on 5 different double T's, with the idea that we're measuring the flange relative humidity and then 2 spots on the stems. And these were installed at the mid depth of each of the concrete elements, because that would have the highest internal relative humidity. And this picture actually shows the probes installed with 1 in the flange, 2 in the stems. So they would be installed, allowed to come to equilibrium. Then we'd connect to these probes with our reader and determine the internal RH. So what did we find? We found that the internal relative humidity within the concrete was between 71.7 and 84.5%. So we're currently at a state that is less than the minimum RH, 92%, for DEF to occur. So what does that tell us? That tells us that we currently are in a state where the DEF reaction will likely no longer occur. And that's beneficial to the owner, because the likelihood of the cracks getting worse is minimal, because we don't have enough moisture in the concrete. So we also did ultrasonic pulse velocity on the double T's. And we do this by sending a pulse through the concrete member, which is received by a transducer on the other side of the concrete element. And if we have the member thickness and the time that it takes for that velocity, for the pulse to go through the member, we get the velocity. And that can be related to the stiffness or the elastic modulus of the concrete. This particular method needs to be correlated to the core compressive strength, which we did. We'll talk about in the next slide. So why did we perform UPV? Because with the continued reaction of DEF, the stiffness of the concrete will decrease. So we were trying to pick up differences in the stiffness of the concrete associated with the DEF. So we did this by taking our UPV and measuring the pulse velocity at different elevations from the bottom of the stem. And we also, at specific locations, extracted cores through the entire stem at the locations where we had previously measured the UPV. Again, we were trying to establish the correlation between the velocity and the strength of the concrete. And we did this on numerous double T's to have a pretty good understanding of the velocity and the strength of concrete. And what did we get? We actually got a pretty good correlation with the idea that the compressive strength of the concrete in place decreased as we went up on the stem. So higher up on the stem had lower compressive strength than lower on the stem. And this is actually consistent with what we would expect from DEF. The thicker sections will actually get hotter, and because of that, we'd expect that reaction to be worse. So we did take those cores, like I mentioned, and we measured the compressive strength and the modulus of elasticity, the stiffness of the concrete. We found on average that the compressive strength of the in-place concrete was higher than the design strength. So that is good news from the owner's standpoint that we have not compromised the compressive strength. However, the modulus of elasticity that we measured, which is essentially 3.0 times 10 to the 6 psi, was lower than we expected for the compressive strength of the concrete. We typically expect this to be about 3.5 times 10 to the 6. So that finding in itself is also consistent with DEF formation and the idea that it decreases the stiffness of the concrete. So we also took additional cores for concrete petrography, and we took a look at those both from cracked and uncracked double T's, meaning the cracked double T's either had fillet cracks or cracks on the face of the stem, or they did not. And we took a look at those under the microscope, and the photograph on the left is from a cracked double T, and we could see those characteristics cracks that we previously saw a couple slides ago, right? We've got cracks filled with ettringite crystals. Now, on the uncracked core, which is the photograph on the right, we do not see that typical classical DEF cracking. So you may be asking why, and we'll get to that later. So the next part of the investigation process was actually doing some thermal modeling. We wanted to know if we had conditions at early ages of the concrete that would be conducive to the formation of DEF. So we modeled the double T's using the geometry, using the heat signature of the mix, using the information we gathered from the supplier related to the concrete temperature at the time of placement and the ambient conditions during placement and shortly thereafter. And we'll put this in our thermal modeling software. And sure enough, we modeled temperatures in excess of 180 Fahrenheit. So that's higher than the 160 Fahrenheit that I mentioned previously as a conservative guideline for DEF not to occur. And the primary contributing factor to that, as we mentioned before, is the quantity and type of cement that was used in the concrete mix design. So we also took a little deeper look into the thermal consequences of these double T's, and we looked at the concrete placement temperatures and the ambient temperatures during placement and shortly thereafter. And what did we find? The two double T's that did not crack in the field had the lowest concrete temperatures at the time of placement and the lowest ambient temperatures at the time of placement and shortly thereafter. And we concluded that these lower temperatures were the likely reason why these didn't crack and the others did. So why did these double T's crack? We have an expansive reaction within the paste of the concrete that is actually restrained internally and externally, but the cracking pattern that we saw, if you remember, most of these cracks were longitudinal. Most of the cracking pattern we saw was not typical of the cracking pattern we see on concrete elements that are affected by DEF. And this photograph shows a more classical cracking pattern when DEF is the primary mechanism. And it's this map cracking, right? We did not see that. And the reason we did not see that is because of the pre-stressing strands in the stem. So the pre-stressing strands put that concrete in compression in one direction, thus allowing that expansion to only occur in the other direction. And that's why we get the longitudinal cracks and not this map crack. And we had unique conditions that led to this cracking. We had the right cement chemistry. We had those high early age temperatures because of the cementitious material used. And going back to moisture, we had sufficient moisture. And why do we think we had sufficient moisture? We feel that the use of the lightweight aggregates, meaning the lightweight actually absorbs a lot of water, so that provided a lot of moisture at the early ages so that the DEF could occur. In addition, they painted the double T's shortly after installation. We found that paint was actually a vapor barrier. So those two things in combination were likely sufficient to keep the RH high enough inside the concrete for the DEF to occur. Now, the existing conditions when we were out there weren't conducive to that, but previously the conditions were likely high enough for it to occur. So we jumped in from there to the analysis. We did do some structural analysis to see the current capacity of the double T's. We found that it was okay for occupancy, but not as a storm shelter. And that's important because they had built this to be used during tornado events. So they could use, the kids could use the gym for play and whatnot, but not as a storm shelter. So we started to do design options. The do nothing option was obviously not reasonable and not appeasing to the owner, right? They designed this and built it for a storm shelter. So the do nothing option wasn't an option. We also were looking at other repair options with the end goal to restore the structural capacity consistent with the ICC 500 shelter loads. Ultimately, the owner decided to remove and replace, which is a reasonable option. So our work stopped at WJE and they ended up removing and replacing. In the end, we've got some lessons learned here. And one of the lessons is the importance of the investigation process. So this process is really needed to help us identify the DEF and also uncover the unique conditions that led to the DF. It helped us understand the significance of the cracking, and also helped us with repair options, and ultimately educate the owner of related to the implications of finding DF. It's also important to note that not all cracks are this significant, but the process for the investigation is the same. And DEF, as I mentioned before, is very rare, and it manifested from very unique. It manifested it as unique cracking conditions. And the last thing I want to highlight is the communication that's needed with the client in this particular situation. That the finding a DEF was important, but the implications of that to the performance of the structure and the structural capacity had to be communicated to the client. And as you can imagine, the scope of work as we were investigating was very fluid. So we had to keep the client updated with the timeline associated with that, and ultimately the significance and limitations of any findings we have. And then we needed to clearly communicate with the client as well in terms of the repair option. And that was a very important part of this process, and ultimately leading to the decision to remove and replace. And with that, I'm actually going to pass it over to Josh. He has another very interesting example where he employed the investigative process to help uncover some unusual conditions. Take it over, Josh.
Thanks, Todd. So the case study I'll be discussing starts with some unexpected movement in a concrete tilt-up wall panel. So what's the issue? Tenants had complained to the owners that their building was making unusual noises. And so the owner took some prompt action to investigate and reported a vertical crack in between two panels at the sealant joint, if you were to look from the exterior of the building. So there was no other signs of distress. Upon our arrival, our initial scoping site visit, we determined that the reported cracks were actually the sealant joint ripping apart between two adjacent wall panels. We also saw that the tilt-up concrete wall panel was tilted, but a little bit more so than usual. We asked for a ladder to take a look at the roof framing from within the building and asked if the owner had drawings so we could make sure we understood how this single-story building was framed. So here's a picture of the crack, and as you can see, this is not good. When we lifted the ceiling tile and poked our head up above the ceiling tile to observe the roof framing, this is what we observed. The joist had pulled out of the wall panel, which is obviously supposed to support the wall framing. So I've talked about joists and wall panels, so let's take a second to describe what it is that we are actually looking at and how these parts fit together. The tilt-up wall panel, which has its name the way it's constructed, has an intentional void pocket, and that's so that the roof framing can be supported within the wall panel. In order to connect the roof framing to the panel, there's an embed plate that's cast into the wall using headed studs, and the joists sit in the void pocket and then are welded to the embed plate. The joists then support a metal deck, which then supports the concrete infill. Then you've got the roofing material installed all over this. Then you have your interior finishes, and this consists of the cold framing or metal studs that can go all the way up to the roof. And then you have the suspended ceiling that's suspended from the framing, and then you have your drywall. So when we poked our head up above the ceiling tile, we saw that not only we had a number of joists that were no longer supported by the wall panel, but the fact that they were pulled out caused them to essentially drive out the wall panel. Now, mind you, this is as we have our heads stuck up above the ceiling tile, so we could actually see the cold framing bending as we were staring at it. These members here were once vertical, but now have buckled. So this is a failure, and it's a unique condition. We immediately assisted in evacuating the building, and as soon as we had done that, the soffit had deflected due to the deflecting joists, and that immediately caused the curtain wall or the glass enclosure to shatter. So perfect timing. Now, during unique events like this, the investigative process is still followed, but as you can imagine, it's not quite so linear as Todd presented. So this one, we started out with our initial site visit, and within hours, we were trying to design a repair. So what had happened? Based on our review of the drawings and confirmation of the field conditions, there were about 4 joists that had pulled away from the tilt-up wall panel, and this is the wall panel here in red. And here is the beam on the interior portion of the building that supports the roof joists on the interior side. So we had the 4 joists that are supported on the beam on the west side. They were once supported by the wall panel on the east side, and all of the other joists in the surrounding vicinity seemed to be stable. But the 4 joists continued to drop. So here's our profile of the roof framing again. The 4 joists had pulled out of the wall panel, and they were pushing and rotating the panel outward, and the cold framing was bending under the weight of it all. I'm going to remove the non-structural elements here, and so you can demonstrate the mechanism that we're seeing. The embed plates not only keep the joists in place so it can bear gravity loads, but it's also there to resist horizontal loads. So when properly constructed, these embed plates have a lot of capacity, and it takes a lot to fail one. So what we had seen is the joist pulled out of the wall panel is driving the panel outward. Here's a close-up of the end of the joists that were once supported by the wall panel, and I should say that these photos were taken after the building was stabilized. Within hours, a contractor was on site to support what we could of the exterior wall. And here's some photos of the wall panel being stabilized with lateral braces. So here's how the contractor approached the roof stabilization. We had to come in to the building from the north where the joists were still securely attached to the stable wall panels, cut out the partition walls, and began shoring the adjacent framing that was stable. So this provided a protected area from which the contractors could work from, moving south into the area that was affected. So going back to the floor plan, we braced the external wall first, and then we came in from the interior. Now, one thing that had come up in our quick review of the drawings and our field observations is that the building is singly sloped and drains from the east towards the west. So our question was, how about the new slope in the roof caused by the collapsing roof? The location where the roof joists were falling was once the high point, and now it represents a significant low point and can pond water. And of course, it had to happen the weekend prior to one of the heaviest rains we'd seen in this all season. So this is the aerial view of the roof, and you can see the panel stabilized. And here's the intended direction of the roof framing. And fortunately, we were able to cut out the roof framing so that the roof could drain appropriately. So what happened to cause all this is you can see in this photo of the embed plates, we have studs on the bottom of the plate that are intended to be buried into the wall. And we have outlined here a clue that the plates weren't installed as shown on the plans. So here's our profile again, and here is the embed plate. And as you can see now, the embed plate was constructed to be outboard of the intended location, and this resulted in a significant reduction in breakout strain. In addition to that, the joists were not positioned properly, so they did not have enough concrete to bear on. So they were positioned actually outboard of the wall. And so the failure mechanism here involved a breakout of the concrete surrounding the embed plate, which caused the joist to deflect and push the wall out. We had said earlier that often failures are the result of more than one mechanism. And certainly we had construction issues, but what were some other potential contributors? Perhaps the Great Texas Freeze of 2021, where this was located, where we had loss of electricity and sustained cold temperatures for some time. We also had cyclic thermal and rain loading. The repair design was rather straightforward, and in this case, we lifted the roof framing with hydraulic jacks, which I'll just show you a few pictures of that. We rotated the wall back into place and installed new structural steel. So here's a couple of images of that roof being raised and the wall panel being rotated back into place. And here's the typical repair that we use to install and support the faulty embed assembly. So the repairs we designed were able to correct the construction issues, and as part of the investigative process and detailed site investigation, we found that this condition actually exists in other locations. So we were able to implement that repairs in other locations of the building that had not yet collapsed. What are our lessons learned? First, we'd like to point out that not all cracks and sounds you see or hear in your buildings are this significant. But the red flags that the owner was paying attention to were the sudden changes in conditions. And the investigative process helped us piece together these clues. Another lesson is that it took time for this condition to manifest, and we wouldn't have necessarily caught this if we had just performed a routine structural inspection that didn't include a view of the interior. A big takeaway is that the owner was very responsive, and this helped them save the building. We had an established relationship with that owner, as well as the contractor who arrived on site, so those relationships were very helpful to have in place. Todd and I are going to wrap up with some closing thoughts, and I'd like to bring us back to the question we posed at the beginning, which is what constitutes a failure? The ones we presented on were certainly failures, and they were exceptionally rare. I'd like to point that out. These are not common. And the parties involved were appropriately responsive, which helped us solve this problem. But you may still be asking yourself, how do I know if that crack that I'm looking at is typical or unique? There's not a simple answer, and some of the components of the investigative process will be required to provide answers and solutions. And often, the first two components that Todd talked about, the initial site visit and the document review, sometimes that's sufficient to understand the complexity of the problem. And we typically don't know if the other components will be required until we at least perform these two. We like to think about it as like you're going to the doctor, right? Your initial site visit is your initial appointment, and the document review and the background history, that's you sitting in a waiting room going through 35 pages of seemingly unimportant information that you're filling out. But those are actually quite essential to the doctor. So the investigative process is important, but there's still some additional things that you can be aware of as a building owner. So potentially concerning observations. You want to be, you're right to be concerned when you have conditions that are worsening, meaning they increase in size and severity. Are all building components moving more than normal? These are things to be concerned about. Are there unusual noises that aren't just the HVAC acting up? When in doubt, seek a professional. Finally, we'll leave you with some recommendations on how to think about regular maintenance, which is necessary for every structure. It's important to become educated on what conditions are typical and why they occur. A good reference is down here at the bottom right, the Visual Condition Survey of Concrete. It's a good guide. It's also important that you address deterioration in an appropriate time frame. So before you repair it, though, you want to know why it occurred, and otherwise you may be making the repair again sooner than you anticipated. You also want to engage an engineer potentially to help you look at options for the repairs. A big one is avoiding moisture inside buildings. Moisture is intended to be outside of the building, and we should keep it that way by maintaining, repairing, and replacing joints and sealants. Finally, we want to keep those in maintenance and inspection records. They can be a critical part of the investigation. With that, I'd like to turn it back over to Liz to take questions.
All right, thank you, Todd, and thank you, Josh, for the great presentation. All right, let's take our first question. This is, I believe, for Todd. Is cracking of the double T stem and fillet always considered unusual, or was the large width of the cracks in question what tipped you off to the fact that cracks were more than a typical deterioration condition?
Yeah, that's a very good question. And we see cracks in the fillets of double T's quite frequently due to lifting, and those cracks are actually typically much tighter than what we saw in this particular case. So that kind of clued us that there's something else going on with the idea we had cracks up to 1/8 of an inch. We would not see crack widths that wide for other reasons.
Okay, a couple more questions for you, Todd. At what point did the team assess whether there was an immediate threat to flange compressive strength stemming from DEF?
Yeah, that's a great question. And we assessed that very early on. The no occupancy was put in place. It was kept in place until we had a chance to get our eyes on the structure and our hands on the structure, and then do an analysis to understand if they could occupy the gym or not. And that was done very shortly after our site investigation. So we did turn it over so they could use the gym for normal activities, but not for tornado events.
Okay. What is the required RH to have the possibility of DEF? Is it 90 or 95%?
It's generally understood in the industry, it's about 92%. And to get more accurate than that, research studies would have to be done on the exact cementitious materials in the concrete being used. But that is generally understood to be around 92%.
Okay, in case study 1, how long did the investigation process take? Did you write a report summarizing the findings?
So the investigation took approximately, I would say, around 3 months before we got stop work. And we were actually giving the client and the project team updates on a weekly basis in terms of our findings and the implications of those findings. And we were in the process of actually writing a report when we got the stop work. So our client was privy to all of the work we had done, the results and implications, but a final report was actually never written.
Okay. 2 more quick ones for you, Todd. To what extent did you account for reduction in member capacity when taking cores in terms of both frequency and location?
Yeah, I think I understand the question. And so with the core strength results that we did get from the double T's, we did do an analysis on the results to get an equivalent in-place design strength following the guidelines of ACI 214. So we did that before we actually used that information in our structural analysis to determine capacity. I think that's where that question is going. If not, feel free to follow up with clarification.
Okay. What software did you use for the thermal modeling?
We used software called 4C Temp and Stress to do the thermal model.
Okay, these are coming rapid fire now. Does WJE have a petrographer on staff, or is that analysis performed by an outside firm?
Yes, we do. That's one of the benefits we have. All of the work done as part of that project was done within WJE, meaning the non-destructive testing, the chemistry, the petrography, the structural analysis, all of it was done within WJE. And that's one of the nice things about working here is we do have all those capabilities.
Okay, jumping now to case study 2. What was keeping the joists that pulled away from the wall from falling? Did the roof deck support those joists, or was it pinned against the wall?
Yeah, it's a very, very good question. So actually what we didn't show on the wall panels was that they were actually sitting on top of some piers that were slightly underground. Okay, and exterior to the building, we had a pavement that was somewhat locking in that wall panel. So there was just enough support to keep this as a slow, collapse essentially. And so we were able to short in time. Certainly with some additional load over the course of the weekend with the water load, we would not have expected that to remain in place. So this was certainly a quick work in progress.
Okay, another question for you, Josh. How long after the building was in use did this occur?
The building was approximately 55 years old at the time. So this is the building had been had seen a thing or two before this event had occurred.
Okay, this is a question again for Todd. I believe. Would a different concrete design mixture have prevented the double T cracking?
Yes, potentially. A concrete mix design that would have a lower heat signature, meaning that would generate lower amounts of heat, and potentially the incorporation of SEMs would have likely prevented the DEF from occurring.
Okay. Going back to Josh, was the tilt-up wall contractor held responsible for the misplacement of the joist bearing hardware?
Unfortunately, no, Liz. Being 55 years after construction, we didn't even know who the tilt-up wall panel manufacturer was, and most likely they were well out of business.
Okay. Falling back to Todd, is there a reason you didn't use a Swiss hammer rebound test on the double T?
I want to answer that appropriately. I don't feel it would have been a useful tool in this particular situation. And I guess if that person has more detail behind their question, I would gladly answer. But in this particular case, I wouldn't feel it would be a useful tool to accomplish what we're trying to accomplish with our investigation.
Okay, we're going to extend 1 or 2 minutes past the end of the hour just to take a few more questions. If you're not able to hang on with us till the end, look out for an email from us this afternoon. Some more information's on the screen. And if you are able to hang on, thank you very much. We appreciate your extra time today. Okay, this is for Josh as well. What was the time between first on-site and the repairs being installed?
It was approximately 5 or 6 hours. So this was a little bit steady of a or slow start. What was interesting is the building noises had actually occurred earlier that day, and the client, I had mentioned that they were quite unsettled by the noises. They tried to call me on my cell phone actually first, and interestingly, we were on top of a building and couldn't answer it. But the client was very responsive. He actually went and parked inside of our office building to try to get our attention. And so they, without that dogged attention, we might not have been able to look at it that evening. So responsiveness was really, really important for this one.
All right, this one is for you too, Josh. How did you know it was safe to look inside the cavity above the false ceiling to see the conditions? Some level of risk appears to be involved in just investigating the structural deficiency.
It's a very good question. And at the time we did stick our heads above the ceiling tile, we didn't really know what was going on. So we had not been able to make that determination at that time. But once we understood it, we immediately evacuated the building and were able, to approach the building from the portion of the building that appeared to be stable, so we could understand the structural framing. But it goes back, Liz, to the importance of looking at the documents and understanding how a building, particularly 55 years old, was framed. That was a very important step in the investigative process.
Okay, this will be our final question. This person said, my question comes from a building owner perspective. How do you help inform an owner with how much investigation is necessary to get to a recommended solution? Said another way, how do you try to balance the cost to the owner to perform an investigation versus the benefits provided from the investigation findings?
I think I'll take the first stab of that, Josh, and maybe you can add to it. Brad, sure. Thank you for the question. I think that comes down to communication with the owner. Obviously, with every crack, every spall, every delamination, we do not have to do the level of detail that we did on our 2 case studies, right? But that's up to us as engineers, consultants to the owner to effectively communicate what the problem is, and if there is additional investigation that's needed, what are they going to learn from that and how much it's going to cost, right? And we have to do that throughout the process so that the owner can make an educated decision whether that money is well spent or not, right? And that's how we proceed. And Josh, do you have anything to add to that?
Yeah, I will also add that, the investigative process is there for a reason. We don't necessarily always know at the get-go how much, how long, what kind of testing we need to perform. So we're very cognizant of, we have budgets within which to work, right? And so we typically like to use the first steps of that investigation to help walk the owner through what potential scenarios may exist. And, we try to learn as much as we can about what the options might be early on, so that, as you said, Todd, owners can make informed decisions.
Okay, well, thank you, Josh, and thank you, Todd, for the great presentation. Thank you all for joining us and for submitting so many good questions. So again, thank you so much for your time, and we hope you have a great rest of the day.